The sun is shining, the birds are singing, and we're stuck inside doing physics past papers. Let's do this as quick as we can then, shall we? This is AQA, A-Level Physics 2020, Paper 2, Year 2 content. As per usual, I can't show the paper on screen, otherwise AQA will get my whole channel deleted as they nearly did in the past. But links to the paper and the mark scheme are in the description. 1.1, we have this heating curve for this metal. We're being asked what the melting temperature is. Of course, we're looking for this temperature here, and that ends up being 28 degrees C. Just have to read off the graph. Easy peasy. 1.2, how does the energy transferred change the arrangement of the atoms between TA and TB? So this is TA, this is TB. First thing we say is that temperature is constant, so we're talking about change of state. But we're not being asked about the whole metal, we're being asked about the arrangement of the atoms. So the mark scheme has some weird ways of putting it, but we can say that the energy transferred breaks some bonds between atoms. Now, they're being very picky. They say if you say that the bonds are broken, you're implying that all the bonds are broken, and that's not true, is it? Because otherwise it would become a gas. So you've got to be careful when saying that. So you get a mark for that. We could also say that atoms are now able to move past each other rather than vibrate around fixed position. Now the mark scheme says, first way of putting it is, it reduces the number of nearest atomic neighbours. I mean, I've got to be honest, I've never heard it put in those terms before, but there we go. That's what they say. Also says that it allows the atoms to move their centre of vibration. Okay, that's saying that they're able to move, so yeah. It's all very wishy-washy. I hate questions like this, so let's move on. 1.3, we've been asked what happens to the potential energy and kinetic energy of the atoms during this time interval. So we know that during a change of state, Ke stays constant because the temperature isn't rising. We know that Ek is proportional to temperature, but Pe increases. But we know that Pe increases, the potential energy increases. 1.4, how does the motion of the atoms change between TB and TC? So we do have an increase in temperature, and actually we've just answered that above, haven't we? Therefore, we could say mean Ek of atoms increases. But we do actually have to have that mean in there in order to get the mark. So be careful with that as well. 1.5, we're given a mass of 0.25 kilograms. We're being asked to find the specific heat capacity when it's in a liquid state. So let's look at our graph again. We're not looking at this bit. We're looking at this bit here. This is temperature and this is time. So the time at which it starts heating up at a liquid state is 11.2 and the graph ends at 14.8. What about the temperatures? Well, we said that was 28, and at the top that is 110. So we have a change in temperature of 82 degrees C or Kelvin, doesn't matter, same thing in this case. And we have a change in time of 3.6 minutes. Let's times that by 60, and we get 216 seconds. Okay, so let's crack out our SHC equation. Energy is equal to mc delta T. And we know that it's being heated with a power of 35 watts. So that is 35 joules per second. So we can say that energy is power times time. We're looking for C, so therefore we're going to take m delta T over the other side. So that's going to be our power of 35 times our time of T16 divided by the mass, 0.25, times our change in temperature, 82. And that gives us 369. Well, the unit is going to be joules per kilogram per degree C or per Kelvin. Oh, we've been asked for the units as well. There we go. You would actually get the mark for that, but let's go with per Kelvin instead. Doesn't matter though, you get the mark either way. If you go to 2 sig figs, that's 370. So now we have a bunch of latent heats for different metals. Which one is this metal that we're dealing with then? Well, let's crack out our equation. E is equal to ml. Again, Pt is equal to ml. Therefore, rearranging this, we just want m over the other side. So Pt divided by the mass. So we have our power, but what's our time this time? It's not the same time because we're talking about the time to change the state of our quarter of a kilogram of this metal. And I can see that the time is going from 1.8 to 11.2. Of course it was, because that was our beginning of the time previous question. So therefore, we're going to say 11.2 take away 1.8. We end up with 9.4 minutes, but then we have to times that by 60 again, and that gives us 564 seconds. Okay, so therefore our specific latent heat is going to be a power of 35 times our time of 564 seconds. Divide that by our mass, and we end up with a specific latent heat of 78,960. So let's call that 79,000 joules per kilogram, but our table is in kilojoules per kilogram, so that's 79 kilojoules per kilogram. Of course, that is around about 80, so therefore it is going to be gallium. Question 2, gravitational fields. We have effectively Kepler's law, which is T squared is proportional to R cubed, but it's T squared equals KR cubed instead. So we're effectively being asked to find K, so we need to prove Kepler's law, Kepler's third law, we should say. But that is the only one that we deal with in bog standard AQA physics. So what we say is that GMM over R squared, Newton's law of gravitation, it's a force that supplies centripetal force, so we could say mv squared over r, but because we're dealing with time period, then we're going to go with m omega squared r instead. One of the m's cancels, one of the r's goes to the other side. If you're not concentrating, you might just like cancel them out and just end up with r, but that's not true, is it? We know that omega is equal to 2 pi f, or in other words, 2 pi over t over the time period. So let's pop that in. So let's write it out. R cubed is equal to 2 pi over t all squared. And so that's equal to 4 pi squared over t squared. So then we just need to rearrange everything. So I'll tell you what, let's flip everything on its head. So we end up with t squared over 4 pi squared is equal to r cubed over gm. We want t squared by itself, so let's pop the 4 pi squared over here. And sure enough, we end up with 4 pi squared over gm times by r cubed. And this is our K. 2.2, we have moons of Uranus. Calculate the orbital radius of Umbriel. So if we know that t squared is proportional to r cubed, then we can say that t1 over t2 squared, that is equal to r cubed over r cubed. I've kind of skipped a step there, I guess. We could say that t squared over r1 cubed is equal to t2 cubed over r2 cubed. So we're looking for the radius of this. So let's rearrange to find r cubed, r2 cubed that is. So we end up with r1 cubed divided by this ratio here, or we could times by the reciprocal of it. So let's do that, times t2 over t1, and I'm going to square that all together as well. So that's equal to 1.29. We don't actually have to do the times 10 to the 8 because, well, it's just all relative, it's just ratio. So whatever answer we end up with, we know it's going to be times 10 to the 8 as well. Little shortcut there. Times by, and again, we don't need to turn this into seconds because it's just all relative. There's the cube there, of course. And I get an answer of 18.5 for that. And so therefore, cube rooting that, we end up with 2.65 or 2.7 times 10 to the 8, of course. If you do take that shortcut, just remember to make everything right at the end. Of course, there is a little bit of a shortcut, isn't there? We could go from here and we could say that R2 is equal to, well, R1 to 3 over 3. So that just ends up being R times the ratio of the time periods to the power of 2/3. That's a little shortcut. Doesn't matter which way you do it. Yeah, slightly quicker, but only do that if you know what you're doing. 2.3, we're being asked to find the mass of Uranus. Okay, so we have our equation from before. T squared is equal to 4 pi squared over gm times r cubed. We're looking for m. So what we're going to do is swap around t squared and m. Therefore, m is equal to 4 pi squared r cubed over g t squared. So popping numbers in nice and careful like. So 4 pi squared times the radius. We can use Miranda or Umbriel, doesn't matter. Let's go with the one that we've actually been given. So that's cubed divided by g. But now we do have to turn this into seconds. So 1.41 days times 24 hours times 3,600 seconds in every hour, and that is squared. And we end up with an answer of 8.56 times 10 to the 25 kilograms. And it should be to 3 sig figs because our data was 2 3 sig figs. 2.4, we have more moons. We're being asked which one has the greatest escape velocity. Escape velocity, we say that KE is equal to PE or GPE. So we say half mv squared is equal to GMM over R. One of the m's cancels. We're looking for V. So rearranging this, we find that V is equal to the square root of 2GM over R. Now, if we're just looking for the greatest escape velocity, then we don't actually care about what the units are. We can stick whatever we have in there so long as we're consistent. And actually, we can go one step further. We can actually remove G from it as well. So we can say that V is proportional to the square root of M over R, because of course we don't care about the 2 either. And yes, we've been given the diameter, but we know radius is proportional to diameter, so we can replace it with that. So let's go for aerial, whatever. So we can say that square root of, we can just say 1.27, we don't need the powers of 10, divided by 1.16. Operon, we say square root of 3.03, don't need the times 10 to the 21 again, divided by 1.52, don't need the times 10 to the 6. And titanium as well. Okay, here are my 3 answers. So we can see that, relatively speaking, titanium will have the greatest escape velocity. Of course, you could actually find out the actual escape velocities if you wanted to, but because we're just comparing 3 different values, it's all relative. We don't need to do that. Okay, 2.5, we have an object that can go 1 meter high on the Earth, then on aerial, we're being asked to prove that if it goes higher than 100 meters, so basically we're just being asked what height is it going to get to. So if it's a spring-loaded mechanism, then we can say the energy stored in the spring is going to be the same, and so whatever GPE that we have here, that's also going to be the same GPE that we have here. It's just going to be at a different height. Now, we are dealing with a planet, etc., aren't we? And so we should say that really, there should be change in GPE, of course, shouldn't it? So we could go down the route of, well, find out the difference in GPE. So energy at the surface compared to energy 1 meter high, etc. That's not going to be a big difference though, is it? And then we have the same for aerial, but we're talking about such small distances compared to the Earth and, well, aerial as well, that 100 meters is nothing really. So actually, this is one of the few situations where we can say that MGH is equal to MGH. We know that it's the same object, so therefore M cancels. And so we can say that G for the Earth times 1, so therefore it's just G, is equal to G for aerial times the height it reaches. Therefore, the height it reaches should be equal to G for Earth divided by G for aerial. We know that G for Earth is 9.8 at or near the surface. What about for aerial then? Well, we know it's equal to GM over R squared. If we're talking about the radius of the planet, so 6.67 times 10 to the minus 11 times the mass. What did we say that was? Going back up, 1.27 times 10 to the 21 divided by the radius. We were given the diameter of 1.16, so we're going to say that that is 0.58 times 10 to the 6 instead, and that's squared, isn't it? Tidy up some powers of 10 maybe, minus 11 and 21, so that just makes it times 10 to the 10 on the right hand side. Could tidy up the times 10 to the 6 to make it 12 and then divide, but I'm not going to do that. So I end up with a gravitational field strength of 0.25 meters per second squared, or newtons per kilogram, same thing. And so therefore, I want to know what this height reached is. So the height is going to be equal to 9.81. Let's go with that. Divided by 0.25. So basically it's 4 times bigger. So no, it's definitely not going to happen, is it? Because we can see that it's not going to be, well, it's going to be around 40, isn't it? So therefore, no, it's not going to get higher than 100 meters off the surface. 3.1, we have a mass spec. Love a mass spectrometer. Draw 2 labels on the diagram to show the directions of the electric force and the magnetic force. Okay, so we have our particles going through this aperture. They're going like that through there. We're drawing it at A. It is a positive ion. and we're told the magnetic field is going into the page. Okay, so let's get our left hand out. One of the few times where it would be good to have a camera in this situation. But I tell you what, maybe it's easier to go with electric field instead. So we're told that the electric field, so this is B, electric field is going down. There we go, maybe let's go with that instead. So we can see that the electric field is going down. Electric field lines show the direction of force on a positive charge, so therefore that is going to be our Fe. And so if it's going straight through, then we know that that must be balanced with the magnetic force going in the opposite direction. If you get your left hand out as well, you'll have your first finger going into the page. You'll have your second finger, which is current, but it's conventional current, so it is the flow of positive charge, so that's going to the right, and so your thumb will end up going upwards. 3.2, we're given a speed of 1.5 times 10 to the 5 meters per second. We're given a flux density of 0.12 Tesla. We're being asked to find E. So this is fairly standard. We know that if it's going straight through, we know the arrows are going to be the same size, therefore the forces are going to be the same size. Therefore we can say that BQV, which is the force due to the magnetic field, is going to be equal to the force due to the electric field, which is EQ. Of course, you probably know, Q's cancel, so we end up with V is equal to the ratio of field strength divided by flux density. Therefore, electric field strength is going to be equal to BV, which is 0.12 times 1.5 times 10 to the 5. Don't even need a calculator for that. I can see there's going to be 0.18 times 10 to the 5, or in other words, 1.8 times 10 to the 4. I was going to go for newtons per coulomb, but there you've gone 4 volts per meter. Okay, then we have the particles actually going into the actual mass spec part of the mass spectrometer. So just a magnetic field in this situation. We're being asked to show that R is equal to mv over BQ. Standard question. We know they're undergoing circular motion. So therefore we can say that BQV, which is the force, is equal to mv squared over R. One of the V's cancels. And so therefore, rearranging this, swapping over R and B and Q, we end up with it. Easy. 3.4, the ions of different masses are deflected. Singly charged ion passes through the small aperture. Calculate the distance between the small aperture and the point at which it hits the detector surface. So, what you're going to remember is that there's the center of its circular path. It's going there and there, so it's going 2 radii. So we need to find the radius and then double it. So we already have the question. That's nice. It's a lithium ion, so we're told that it is 6 and 3. So we're going to say the mass is 6 times 1.67 times 10 to the minus 27 times the velocity, 1.5 times 10 to the 5, divided by the same flux density that we had before, so magnetic field makes sense, times the charge. It is just singly charged. If you made a mistake in this question, you might have done 3 times 1.6, but no, it's got 3 protons, but it's only missing 1 electron, so therefore it's only going to have a charge of 1 of these. Let's sort out some powers of 10. Minus 27 and 5 just gives us minus 22. And then we have minus 19 on the bottom, minus 22 on top. So we can just say that this ends up being times 10 to the minus 3. And we end up with an R of 0.078 meters. But like we said, we want the diameter. So we times that by 2 and we get 0.16 meters. 3.5, we have a different type of mass spec. Oh, this is going to be a timing one, this. So we're determining the speed of the ion when it emerges. So we have EV is equal to half mv squared. Whenever you have a charged particle that's being accelerated through PD, that's the first thing we write down. EV equals half mv squared. We're looking for V, so rearranging this, we end up with V is equal to the square root of 2 EV over m. Make sure you don't get your V's mixed up. Okay, so that's going to be equal to the square root of 2 times, singly charged again, so 1.6 times 10 to the minus 19 times. Now, be careful here because the sample is halfway between the anode and the cathode. So actually, it's going to be at a potential of minus 3,000 volts. It's going to minus 6,000 volts. So actually, the potential difference is going to be 3,000 volts. What is the mass going to be? Well, it's a lithium-7 ion this time. So it's going to be 7 times 1.67 times 10 to the minus 27. Okay, I think we can tidy this up quite a bit. We have minus 27 on the bottom, minus 19 on top. So this can become just times 10 to the 8. But then we have 3,000 as well. So we might as well just call that then times 10 to the 11. And then we can just say 2 and 3 just becomes 6. So let's write this out again. So square root of 6 times 1.6 times 10 to the 11 divided by 7 times 1.67. And I end up with 2.9 times 10 to the 5 meters per second. Mark scheme gives 2.8, but that's because of the rounding error with their mass. They calculated that first. 2 sig figs. 3.6, lithium-6 and lithium-7 ions are produced simultaneously. For each type of ion, the time interval between production and detection is measured. Discuss how the masses of the ions can be deduced from the measurement of these time intervals. So let's write down our thing again. EV equals half mv squared. We know that E is constant for both because they're both singly charged. They have the same PD, they're accelerated through the same PD. And so therefore, if we're thinking about proportionality and relationship, forget about the half as well, we can say that moving mass to the other side, or V squared to the other side, doesn't matter, but let's go with V squared. V squared is inversely proportional to the mass. So I guess we could say that V is proportional to 1 over root m, or m to the minus a half. Therefore, greater mass, that's going to be the lithium-7, isn't it, equals slower speed, therefore takes longer time to reach detector. Guess we should probably be explicit with regards to our stuff above. So we can say charge is the same, V is the same, therefore all ions have same kinetic energy. So then we go from there. Electricity, 4.1, calculate the RMS voltage of the supply. So we have a peak voltage of 15 volts. We know that the conversion factor is root 2. It's going to be smaller. So therefore it's 15 divided by root 2. And that gives us 10.6, or technically it should be 11, but okay, fine. Let's go to 3 sig figs there. You would get the mark for 11. Okay, we have a trace on an oscilloscope. Determine the Y voltage gain of the oscilloscope. So basically, what is the scale? So we can see that to get to the peak, we're going to 1, 2, 3. So it's going like that. So therefore, we know that if we're ending up with 15 at the top, then every little division must be 5 volts. So it's 5 volts per division. 4.3. DC supply gives the same rate of energy. Draw the equivalent of what it would be. Well, we know that we've already calculated it at 10.6. So all we have to do is draw a line at 10.6 volts. That's the DC equivalent. Easy peasy. So 4.4, we've been asked to find the frequency of the square wave. So the frequency is going to be equal to 1 over the time period. We can see that we have this square wave here, and the time period is going to be from here to here. So I can see that that is 1, 2, 3, 4, 5, 6, 7, 8 divisions, or centimeters. We're told that the time base is 5 times 10 to the minus 4 seconds per division. Therefore, time period is going to be 8 times 5 times 10 to the minus 4. So that gives us 40 times 10 to the minus 4 seconds, or in other words, 4 times 10 to the minus 3 seconds. Therefore, frequency is equal to 1 divided by that, and that gives us 250 hertz. So 4.5, we now have a capacitor in there, and we have this trace instead, because it's being allowed to charge and discharge through this capacitor, because the signal is now passing through the capacitor, so it's charging and discharging. Deduce the time constant for the circuit. So we know that the time constant, which is RC, is the time for voltage to get to 37% of an original value. So therefore, if we have 15 volts times 0.37, we end up with 5.55, or let's go with 5.6 volts. And so therefore, I can see that reading off the graph, I'm looking for 5, so there's 5, there's 10, so 5.6 is going to be basically halfway between that square there, so therefore it goes down to there. And we know that the time base is 5 times 10 to the minus 4, and I think it's going across 1, 2, 3, 4. So I'm going to say time constant is 4 times 10 to the minus 4 seconds. There are a couple of other ways that you can do this. Basically, you can just use the full equation and then find out RC from that just by, of course, logging both sides and then go from there. 4.6, we're being asked to state and explain one control setting that would reduce the uncertainty in the value of the time constant. Well, we have more than one decay or one charge here, don't we? So we could make these longer so they fit more of the screen on the oscilloscope, so we can say that we would reduce the time base to make resolution smaller, therefore more accurate values of t obtained. But of course we could also say reduce the Y gain, again to make resolution smaller to obtain more accurate values of V. Now, what's interesting is that the mark scheme says increase the Y gain. But if you increase the Y gain, then that means that we go from, say, 5 volts per division to 10 volts per division. That means that the wave would actually end up being smaller. So I don't really get what they're saying there. I think they might have got that wrong, unless my brain has stopped working or something. Okay, let's move on to a better question for crying out loud. Right. 5.1, state the fundamental force involved with the alpha particle. Of course, it is electrostatic, or actually we should say electromagnetic if we're talking about the fundamental force. You won't get the mark for saying electrostatic. Yes, electromagnetic force results in electrostatic forces, but it isn't a fundamental force itself. Draw an arrow at position X to show the direction of the rate of change of momentum. Of course, what is rate of change of momentum? Another name for it's another name for force. Therefore, if the nucleus is positive and the alpha particle is positive, then the only way that force can be pointing is directly away from it. So it needs to be in line with the nucleus. 5.3, which of these alpha particles are going to be deflected downwards with a scattering angle of 90 degrees, not more than 90 degrees. So you might have got the question wrong. So it's not going to be 4 because that's going to go straight back along. So it's not going to be that. 5, yes, it could be that one. It could go down like that. 6, yeah, it could be that one as well. Do you know what? I'm going to say it's more likely going to be 6, but they will accept 5 or 6, but I'd go with 6. 5.4, we're looking at distance of closest approach. It comes to a standstill. Therefore, we can say that KE is equal to PE. Kinetic energy is equal to potential energy. So therefore, before we even do anything, let's write down half mv squared is equal to KQ over R. So we're being asked to calculate V effectively. K, of course, is 1 over 4 pi epsilon 0, but it is 9 times 10 to the 9. So therefore, rearranging this, we find that V is equal to the square root of 2KQQ over MR. Okay, beastie calculation. Let's be very careful. So 2 times 9 times 10 to the 9, and that is 9.0, so it does work to 2 sig figs, times the charge of the gold nucleus, so it's 79 times 1.6 times 10 to the minus 19. But I tell you what, let's do it all in one go. 79 times the charge of the alpha particle, so that's 2 protons. So 79 times 2 times then 1.6 times 10 to the minus 19 squared. So it's a little shortcut that you can take. Mass of the alpha particle, we're told that 6.8 times 10 to the minus 27, and then we're told the distance of closest approach is 5.5 times 10 to the minus 14. Okay, lots of powers of 10. You don't have to tidy them up, but I think I'm going to have a go. So I'm going to say this is going to be 1.6 squared times 10 to the minus 38. Okay, then we have times 10 to the 9. So that can just become minus 29. Maybe it's worth it, maybe it's not, I don't know, but let's do it anyway. So minus 27, minus 14. So this ends up just becoming minus 41. So minus 41 on the bottom, minus 29 on top. So that ends up becoming altogether plus 12. Okay, so therefore V is equal to, got 2 times 2, so I'm going to just say that that's 4 times 9 times 79 times 10 to the 12, let's pop that in there, times 1.6 squared, divided by 6.8 times 5.5. And I end up with 1.39 or 1.4 times 10 to the 7 meters per second. 5.5, the radius of the gold nucleus is that. So let's say that that's gold. So that is 6.98 times 10 to the minus 15 meters. And we're trying to find the radius of the silver instead. So this is going to be our nuclear radius equation. R equals R0, A to the third. But we are just comparing two nuclei. So we're going to say R is proportional to A to the third. Should probably change these to capital R, seeing that I used that in the equation. So we can say the ratio of the radii is the same as the ratio of the nucleon numbers cube rooted, but I can do that all in one go, can't I? So to the third there. Therefore, all we do is times that by Rg then. Maybe you got a bit of an issue by calling it Ag. Oh well. It's the number of nucleons for gold. So the radius of the silver is going to be the number of nucleons in the silver. That's 107. That's the mass number divided by the number of nucleons in the gold. That is 197. That's the third. And then we times that by the radius of the gold atom. But I'll tell you what, we can just leave it as 6.98 because it's just all relative. And of course, we know it's going to be smaller. And indeed it is 5.695 or 5.7. Even to 3 sig figs is 5.7, 5.70 times 10 to the minus 15. We have to add that on to the end. So there we go. 5.6, all nuclei have the same density effectively. So therefore, what can we say about nucleons? Nucleons have similar masses. That is protons and neutrons. If that wasn't the case, then we'd have quite a bit of variation between isotopes. But we don't. We have a bit, as we know from nuclear stuff when it comes to binding energy and stuff like that. What else can we say? We can say similar volumes. I mean, we can say similar densities, can't we? That's probably the best thing of saying. Another thing you could say is that nucleons are incompressible, and also they have a constant separation. But yeah, it's funny that they won't give you the mark for saying that they have the same density, but hey-ho, what are we going to do about it? 6.1 thermal reactor. We're using uranium-235, and we have a lot of it. What happens when neutrons interact with uranium-235 and 238? So we know that uranium-235 absorbs a neutron to become uranium-236, which is unstable and decays into 2 daughter nuclei and 2 or 3 neutrons. Uranium-238, though, absorbs neutrons without undergoing fission. It just sits there. We can also say that it scatters neutrons. 6.2, the amounts of uranium-235, 238 decrease due to decay, as we know. Sample of uranium ore today contains 993 grams of uranium-238. And we have a time of 2 times 10 to the 9 years. That's a long time. We are going to 3 sig figs here, so let's make sure that we're consistent. We have the decay constant, 1.54 times 10 to the minus 10 years to the minus 1. Great, so we don't need to convert any times because we have our consistent time units. So let's crack out our decay equation. We can do this for activity or number of nuclei or mass. That's what we're going to be using here. It's equal to e to the minus lambda t. We're looking for m0. Therefore, m0 is going to be equal to the mass divided by e to the minus lambda t. So that is 993 divided by e to the minus 1.54 times 10 to the minus 10 times 2 times 10 to the 9. I think I can tidy this up. So this ends up being basically just minus 10 and plus 9. So this ends up being to the minus 1. So we can just say times 0.2. How about that? And we end up with 1,351 grams, which is about 1.4 kilograms. 6.3, we require a minimum of 3% of uranium-235. The ratio in the ore has changed over time. So 2 times 10 to the 9 years ago, the sample contained 52 grams of uranium-235 back in the day. Okay. Deduce whether the sample had a high enough 235 content to be used back then. Okay. Not an easy question to wrap your head around. So from the previous question, we saw that we had 1,350 grams of uranium-238 but now we know that we have an extra 52 grams of uranium-235 in there as well. So basically, we just want to know what is this percentage compared to the whole thingamabob. So therefore, percentage of uranium-235 is going to be equal to that 52 grams divided by 1,350 plus 52. In other words, the total mass is just the bit divided by the lot. We know that's what any percentage is. And we end up with 0.037 as our number. So that is 3.7%. That is above our 3%. Therefore, yes, it would have been good. In fact, a lot of use that is now. Multiple choice, number 7, ideal gas. We have a temperature of 27 degrees. So let's turn that into Kelvin. So that's going to be 273 plus 27. Of course, that's 300, isn't it? 300 Kelvin. And it's compressed to 1/4 of its volume. So V is changing, T is changing. Oh, pressure increases by a factor of 7. Okay, so we're dealing with PV and T in this situation. So PV equals nRT, N and R are staying constant. Therefore, we can say P1 V1 over T1 equals P2 V2 over T2. We're looking for T2, so just cross multiplying everything, we end up with T2 is equal to P2 over P1 times V2 over V1 times the original temperature. So it's going up to 7 times its pressure, so that's going to be 7. It's going to 1/4 of its volume, so that's going to be times 1/4 and then times by 300. So 7 divided by 4 times by 300, and we end up with 525 Kelvin, but we want it in degrees Celsius, so to take away 273, and we end up with 252 degrees Celsius. Our answer is D. Question 8. Oh no, I hate these questions. Okay, so we have lots of gases, different temperature. Volume of X is twice that of Y. Okay, so let's say that Vx equals 2 lots of Vy. X is at 100k, Y is at 400k. There is no net transfer of particles between the flasks. Okay, X contains gas of mass M. How much mass is in gas Y? So the mass of Y is what? So if there's no net transfer of particles, that means that the pressure must be the same. Pressure of X must be equal to the pressure of Y. So let's crack out PV equals nRT again. The only thing that's not changing here is R. N is changing because they have a different N, don't they? We can say that P is proportional to NT over V. Okay, so that means we can say N of X times the temperature of X divided by the volume of X is equal to the same for Y. Gosh, my Y's look like X's. No. Okay, what do we know? We know that the volume for X is twice as big as Y, so we can say 2 and 1, so that just disappears there. We can say that the temperature of temperature of Y is 4 times greater, so we can just replace that with a 4. So therefore, just rearranging this, we end up with the number of moles in Y being equal to the number of moles in X divided by 2 times 4. So it should be 8 times less, so the answer is A. Of course, the number of moles is going to be proportional to the mass. That's what they're really asking. Not more gases, no. Okay, so we have a second sample contains 2/3 of a mole, right? So number of moles in P is 1, number of moles in Q is 2/3. We have the temperature, with the temperature of P being, 1 effectively, and the temperature of Q being 2, so it's twice as much. Total molecular kinetic energy of P is E. Okay, what is the total molecular? Right, okay, so we need to find out what it is for Q. So we know that kinetic energy is equal to 3/2 kT. So therefore, if the temperature is double that in Q, we know that kinetic energy is proportional to temperatures, so therefore molecules in Q have 2 times the kinetic energy each, but then we only have 2/3 of a mole, so then we times that by 2/3, so it should be 4/3. So I think the answer is C. 10, ideal gas, yet again. What is the pressure exerted by the gas? But we're given it in terms of CRMS. Okay, so what equation do we have that has CRMS in? Well, it's PV equals 1/3 NM CRMS squared. Okay, so what do we know? We know the volume is equal to A cubed, right? Oh, okay, so that's fair enough. That's fairly easy then. All we have to do is rearrange this. Pressure is equal to, well, they got the 3 on the bottom, so let's just say Nm CRMS squared divided by 3 lots of the volume, which is 3 A cubed. So the answer is going to be D. 11, which one is true? A, does it make it possible to see the motion of air particles? No, not really. You see the effect of it, but you can't see the motion, can you? You can't see the air particles. B, motion is caused by collision of smoke particles with each other. No, we know it's air molecules with the smoke particles. Yeah, it's going to be C, isn't it, therefore? Let's just check D. The motion occurs because air is a mixture of gases. Nah, that's nonsense. So it has to be C. Finally, an easy multiple choice one. 12, we have a potential against distance graph. What does the gradient represent? Of course, we know that potential gradient is the alternative name for gravitational field strength. So therefore, that's our answer. Which one is that going to be? Potential energy? No. Mass of the Earth? No. Magnitude of the gravitational constant? No. D. Magnitude of the gravitational field strength? Yes, it's D. 13. Angular speed of a satellite in a geostationary orbit. We know that's equal to 2 pi f, or 2 pi over t. So that's going to be equal to 2 pi, because we want radians per second. So we know it has to go once around every day. So 24 times by 3,600. And it gives us 7.3 times 10 to the minus 5 radians per second. So therefore the answer has to be B. 14, we have 2 charges. So we're given minus 2q to each charge. So we're going from plus q and 3q, plus 3q that is, to minus q, because we're going down 2q, and plus q. Okay, so let's have a think about the magnitude first of all. Is it going to be 5 times greater? That doesn't make any sense, does it? It can't be. That's really weird that they would give that as an option, whatever. So effectively, we're going from, if we just say that F is proportional to Q times Q, Q1, Q2, we're not changing the distance. So there we go, that's it. So therefore, we're going from 1 times 3 to just 1 times 1. So of course, the force is going to be going down to a third of its original value. That is the magnitude of any of us who can't be B or C. That's nonsense. Is it going to be attractive or repulsive? Well, they are opposite charges now, so it is going to be attractive. So the answer is D. Electric field strength, and we have potential is that. What are the field strength and the potential at a distance 3L from the charge? Okay, so we know that field strength is equal to KQ over, well, they're going with L, so let's go with L as well, I guess. KQ over L squared. Potential is just KQ over L. Of course, we don't care about the K, we're just talking about proportionality, aren't we? And of course, it's the same charge, so that's all we care about. So 3L, therefore, times this by 3. So therefore, the whole thing is going up by times 9. So E is going down by a factor of 9. So therefore, we know field strength has to be going down by a factor of 9. So it can't be A or B. And then we know it's just going to be times 3 here. So therefore, the answer has to be C. 16, what shows the equipotentials near an isolated point charge? A, well, parallel lines, that's not an isolated charge. That's a uniform field. That can't be true. B, they're field lines. That would work, but we're looking for equipotentials. C, yes, they're circular, but they are the same distance apart. We know that they get further apart as we go out from a charge. So the answer is D. 17, positive charge of 2 times 10 to the minus 4 coulombs. Potential is plus 500 volts. What is the potential energy of the system? Okay. This seems a little bit too easy. We know that energy is equal to QV, so therefore it should be 2 times 10 to the minus 4 times 500. I feel like this is a trick question. It has to be 1 times 10 to the minus 1. Can't be C or D. I don't know where they're getting that from. I think maybe that's if you divide it. No, I have no idea. Anyway, whatever. Energy is just joules. So it has to be A. That is the weirdest multiple choice question. Whatever, we'll take it. 18. 2-point charges are 100 millimeters apart. What's the distance from P to X? Yes, I love these questions where potential is 0. So we can say that V1 equals V2. So that means that KQ over R1 KQ1 over R1 equals KQ2 over R2. K's cancel, but then we need to replace R2 with the whole distance, take away that distance that we're looking for. So Q1 over R, we're just going to call it R, equals Q2 over 100 minus R. There we go. All you have to do then is cross multiply everything. Yes, you could probably eyeball this one, to be honest, but it's a good thing to get into the practice of doing. So we end up with Q2 over Q1. So we end up with 100 over R minus 1 because it's just R over R. What I've done is multiply that out, equals Q2 over Q1 again, which of course is going to be, well, 3 over 2, isn't it? So therefore, I'll tell you what, I'll go up here. 100 over R is equal to 3 halves plus 1. So therefore, that makes it 5 halves. So in other words, just 2.5. Therefore, R is equal to 100 divided by 2.5. So I think the answer has to be 40 millimeters. The answer is B. 19. Uncharged capacitor connected to a power supply, constant current of 10 microamps. So that's going to be 1 times 10 to the minus 5 amps. And we have a time of 100 milliseconds. So we can just say that's 0.1 seconds. And we have a PD of 5 kilovolts, so 5,000 volts. What is the capacitance of the capacitor? Well, you know that if we're ever given a constant current and a time, we need to find out the charge. So charge is going to be equal to I times T. So that's 1 times 10 to the minus 5 times 0.1. So that's going to be ultimately 1 times 10 to the minus 6 coulombs. And we know that capacitance, well, Q is equal to VC. So therefore, capacitance is what we know is charge stored per volt, don't we? So it's going to be Q divided by V. So therefore, 1 times 10 to the minus 6 divided by, I tell you what, let's just say 5 times 10 to the 3. And so we're going to end up with, well, 0.2 times 10 to the minus 9, or in other words, 2 times 10 to the minus 10. And so the answer looks like it's going to be A. 20. Parallel plate capacitor connected to a battery. The energy stored is W. The battery remains connected. Okay, if we know the battery remains connected, then we know that V is constant and Q changes. What's changed? Well, the distance between the plates is halved. So D divided by 2. Okay, let's crack out our capacitor equation. That is A delta A epsilon 0 epsilon R. Those are staying the same. The area is staying the same. The only thing we care about is the distance between the plates. So if D goes down by a factor of 2, then that means that capacitance is doubled. So we dealt with capacitance. Now we need an equation for energy. We have 3 to choose from: half QV, half CV squared, and half Q squared over C. We're not going to choose that one for any energy changes when we change something about the capacitor. Which one are we going to choose? Well, we want the one where something is staying the same. And because we know that Q and C are both changing, we're not going to use that one. We're going to use this one here. So therefore, energy is proportional to C. So therefore, if C goes up by a factor of 2, then energy must double as well. So the answer must be C. 21, parallel plate capacitor, dielectric, blah, 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 blah. Which sheet will produce the maximum capacitance? Ooh, okay. So let's look at our equation again. A epsilon 0 epsilon R divided by D. All we care about is epsilon R and D. So let's get rid of that. So we can say that therefore C is proportional to epsilon R over D. So let's do that for each. So A, we have 2 divided by 0.4. And we don't need to turn it into meters because, of course, we're just talking about relative. So we end up with 5 for that. What about B? 3 divided by 0.9. I can see that's not going to be bigger than 5, of course. What about C? 4 divided by 1. That's just 4, so not that one either, not that one. What about D? Nah, that's not going to be any bigger, is it? 6 divided by 1.6. That's going to be less than 5. That's going to be 3.8 effectively. So the answer has to be, first one there, it's A. 22. We have a capacitance, 10 microfarads, so 1 times 10 to the minus 5, let's say. And we have an energy of 4.5 times 10 to the minus 3 joules being stored. We then have a resistance that is going through 25 ohms. Okay, what is the maximum current during the discharge of the capacitor? What's the maximum current? Well, of course, we're looking for V equals IR, aren't we? So we need V equals IR, but in order to know this, we need to know the resistance. We do. We need to know the voltage as well to begin with, the highest voltage. So we need an equation that links together energy, capacitance, and voltage. We saw it just now, half CV squared. Therefore, V is going to be equal to the square root, 2 lots of the energy divided by the capacitance. So that's going to be 2 lots of, well, it's just going to be, well, let's just say 9 times 10 to the minus 3, quick maths, divided by the capacitance, 1 times 10 to the minus 5. And so actually I can just say that that ends up being 9 times 10 to the 2. So in other words, the square root, we don't even need a calculator for this one, square root of 900. So that ends up being 30 volts. Cool. So we have V equals IR. I is equal to V over R. So that gives us 30 divided by 25. Oh, wow. We don't even need to calculate that. Look at the answers. There's only one that makes any sort of remote sense, and that is going to be the 1.2 amps. So our answer is again A. 23, we have this coil. It can rotate. Which statement is correct? A, the forces on the vertical sides of the coil are equal in magnitude and opposite in direction. Yes, that is going to be true. So I guess the answer is going to be A again. Yeah, because, the current is going up on one side, down on the other one. Therefore, the force is going to be in the opposite directions, unequal. Weird. Let's just check the other ones. B, a non-zero couple acts on the coil. Technically not a couple because the force isn't going to be constant as it goes round. I don't like that as an answer, to be honest, but there we go. It's sort of true, but not really, or whatever. C, no forces act on the horizontal sides of the coil. No, they do, just it's not going to make them turn or move because they're fixed, aren't they? As it were, they can't go up or down. D, the forces on all sides of the coil act towards the center. Now, that's just nonsense, isn't it? So yeah, not a very nice question, that one. Question 24. Now, I massively messed up this question the first time. Thank you to Internet Flight Sports for spotting the mistake. Now, I kind of misread the question in a couple of ways, actually. So we have these magnets, and then we have the coil that is being dropped in between. Doesn't matter which way around they are. Now, I assumed that it was going at a constant speed, but of course, it's going to be going fastest at bottom. So therefore, it's not going to be A, it's not going to be B. But if we have a look at C and D, well, C, it's in the middle, and then D, it's on its way out. So you might think, like I did, looking at the question first time round, that the EMF is going to be greater when it's directly in the middle. But if you think about it, if you've seen my video on magnetic fields, this is similar to dropping a magnet through a coil. This is a coil being dropped between magnets. And so actually at this point here, this is where the current flips, and therefore the EMF does too. So actually EMF is going to be 0 at this point. And as it's coming out, it's going to have flipped because of Lenz's law. It's now escaping the magnetic field as opposed to going into the magnetic field. And so therefore it is going to be 0 at that point. So the answer is D. It's in the same position, just flipped compared to B, but it is going to be traveling faster. So that's our answer. 25, alternating EMF. What is the phase difference between the magnetic flux linkage through the coil and the EMF? We know that when we have max flux, we have no EMF. So if we draw a graph of them, we know that they are 90 degrees out of phase. So the answer is pi over 2 radians. The answer is C again. 26, we have the variation with time. Okay, so we know that EMF is equal to rate of change of flux. So I'm just going to say delta BA over delta T. A is staying the same, so therefore we can say that EMF is proportional to the rate of change of magnetic flux density. So therefore, it is going to be the gradient that gives us an idea of what's happening with the EMF. So we have straight lines. So that means it's not going to be A and it's not going to be B because it's obviously the gradient that gives us an indication of what's happening. We have constant gradient between 0 and T1, so therefore we're going to have a constant EMF. Has to be C or D. But which one is going to be bigger, the EMF to begin with or after T1? Well, we can see that the gradient is bigger the second time round, so we are going to get a bigger EMF induced after T1, so therefore the answer has to be C. Yes, it's going to be in the opposite direction, but the magnitude is greater. Oh, this is a classic question. We've seen this like 10 times before. Which describes the force acting on Q after the switch is closed? Well, you should know that, well, current flows through P that induces a current in the opposite direction in Q. So therefore, due to Lenz's law, it's going to want to push Q away. So it's going to be not steady, it's going to be short-lived, because as it goes away, then that force is going to be diminished. So short-lived, undirected to the right. The answer is, of course, D. 28, point source emits gamma radiation intensity, blah, 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 blah. Which graph shows a straight line through the origin? Well, we know that intensity is, well, it's the inverse square law, isn't it? So it's inversely proportional to D squared. Therefore, we have to have I versus D to the -2. So the answer is D. 29, number of parent nuclei in a sample is blah, blah, blah. The rate of decay. We know the rate of decay is the same thing as activity. So therefore, we can say that activity is equal to lambda n. We know that, forget about the minus. So rate of decay is proportional to n. We know that. So the answer has to be A. What a weird question. Finding energy, here we go. What's the mass difference of a lithium-7 nucleus? Well, we need to do 7.01436. That's the mass of the nucleus. Take away 3 lots of a proton. Take away 4 lots of a neutron. And I end up with minus, because well, we know the nucleus is lighter. I end up with 0.04216, and so the answer is B. Finally, 31. Mass of a fuel in fission reactor decreases at a rate of 6 times 10 to the -6 kilograms per hour. What is the maximum possible power output of the reactor? Therefore, we can say that if this is kilograms per hour, we want kilograms per second. So in order to do that, we need to divide by 3,600. And we end up with 1.67 times 10 to the -9. Weird, 1.67, whatever. Now we need to find power from that. In other words, watts, joules per second. So we need to get from kilograms to joules. And so we know that all of that mass in theory has been turned into energy, so E equals mc squared. And so therefore we need to times by c squared. We have the mass per second, now we want to times by c squared again to get joules per second, energy per second. So times by 9 times 10 to the 16, we end up with 1.5 times 10 to the 8 joules per second. We're looking for megawatts. We know mega is times 10 to the 6, so it's 150 megawatts. Hope you found that helpful. If you did, please leave a like. If you want to see some more AQA papers, then click on the card and it'll take you to the playlist. See you next time.